Okay, here we are at podcast 2.4 talking about ions. We're honestly most of the way through our unit. So, page 15, all about ions. We're going to skip around a little bit, but we'll get it all done. So, ions are an atom that has a charge. Just kind of bringing that back from our first podcast. It means that they have the same number of protons as a neutral atom, but they have a different number of electrons. Now, you might want to write this maybe up beside the word ions here, but don't go down into that positive ions space because we need all that space. So ionization is a process where a neutral atom gains or loses electrons to become an ion. It is literally the making of an ion. And a couple other basics that we might have talked about already. I know in the first podcast we also said neutral atoms have the same number of protons as electrons. And maybe in the atom FET, you might have uncovered that the charge of an atom is equal to the number of protons minus the number of electrons. Now, there's going to be an easier way to figure out what the charge of an atom is, but this is always a good fallback if you're in any doubt. So, positive ions, also known as cations, and easy to remember that cations are positive ions. Another way, if you don't like my cheesy puns, is that cations are the kind of ions that have this plus sign in their name. They are cations. And the word for negative ions does not have a T in it. Well, positive ions are neutral atoms that have lost electrons. And because they've lost electrons, they have less negativity in them. They have more positive charges than negative. So overall, the atom is positive. Now, metals are the type of elements that tend to form positive ions. Those are anything left of the staircase, actually including those metalloids that are kind of both sides, are kind of properties of both metals and nonmetals. If they're on the left side, they tend to form positive ions. Now, a little reaction showing the ionization of sodium, helping you see where this charge comes from. We have sodium before the reaction, before the arrow, has 11 protons and 11 electrons. Like we said, it's neutral, and 11 minus 11 gives us a charge of 0. After it's been ionized, you see this electron comes off. We actually don't have minus signs in our chemical reactions. We can see that this is reacted and changed and come off because after the reaction, our sodium is separate from the electron. And now that it's lost this electron and it no longer belongs to sodium, it now only has 10 electrons, and 11 minus 10 is 1. And that is a positive 1. Whenever we put the charge up here, it has to have a positive or a negative sign in front of it, never a plain old number. So, those are our positive ions. Negative ions are known as anions, and you can remember this because their name is literally telling you it's a negative ion, an ion. And these negative ions are neutral atoms that have gained electrons, and because they have more electrons, that's more negativity, and less positivity inside them compared to the negative. They haven't lost protons, though they've gained electrons. That makes them a negative charge. Our nonmetals are the elements that tend to form negative ions, and that's anything to the right of the staircase. If we look here, we see an ionization formula for fluorine. Here it's easy to see fluorine plus an electron. Initially, the fluorine has 19 protons, 19 electrons. That gives it an overall 0 charge. And then with 19 protons still, after our ionization happens, where it adds an electron to it, we have 20 electrons now, and 19 minus 20 is negative 1. Oh, I think I hear a cation in the background someplace. Well, this shows and proves that negative charge. Now, how are we supposed to be able to tell when an atom is going to have a certain charge? Well, let's look at the periodic table more closely, and this is where we're going to skip to the bottom for a second. I need you to write down this octet rule for sure. This rule says that an atom is most stable when its outer energy level, also known as its valence shell, is full with 8 electrons. So atoms are either going to gain electrons until they have that 8 valence electrons, or they're going to lose all of their valence electrons. And they're going to choose whichever way is easiest or shortest, because atoms are lazy. So if this all hinges on those valence electrons, let's go ahead at the bottom of that periodic table and record that each of these columns has a specific number of valence electrons, except of course for those transition metals. The rule says technically they should have 2, but who knows what they're going to decide to have, and some of them can have different numbers on different days. That means that they can have variable charges. If you look up transition metal charges, also known as oxidation states, you can see that you see a whole lot of 2s in here, so that is common, but there's a whole lot of other stuff in here too. So we're not going to bother with those. Don't have to worry about transition metals for right now. But let's look at these noble gases over here, because they already have 8 valence electrons. That means they have everything that they want, which means they are not going to change their electrons at all. That's why they have a 0 charge there. They tend to not react with things because they don't need to. They're already happy and stable. Right next to them with 7 valence electrons, all they have to do is gain 1 electron to get there. And that is definitely what they're going to want to do. The other option is to lose 7 valence electrons, and that's not as easy as it sounds. 6 valence electron column can either gain 2 or lose 6. And so it's going to choose to gain 2. With 5 valence electrons, they could either gain 3 or lose 5. So it's still easier to gain. But once we get to 4 valence electrons, it's equally easy to lose 4 electrons as it is to gain 4 electrons. So this column technically has a choice, but the choice is also kind of made up for them based on where they are compared to the staircase. Remember, our non-metals tend to form negative ions, and so this right side of the staircase is going to tend to be the ones that have the negative 4 charge. Let's try to make that look more like a negative 4. And below the staircase on the metal side of things, we have more positive charges. And so these are the guys that tend to be positive 4s. So, as we keep going, our 3 valence electron column has a choice of either gaining 5 or losing 3. And this is where it becomes easier to lose 3 electrons. Now, you might be wondering how losing 3 gets it to 8. Seems like it gets it to 0. We're going to take a quicker look at that in just a second. 2 valence electrons gain 6 or lose 2. It's definitely going to lose 2. Then with 1 valence electron, they're going to lose that 1. So this is how all of the atoms decide what charge they're going to have. And now let's take a quicker look at what's happening electronically in this atom. So we're going to look at the electron configuration during ion formation of the main group elements. That means everything but transition metals, like we already said. So the metals tend to lose electrons to get this noble gas configuration, to get that 8 valence electrons. And we said earlier they're going to lose all of their valence electrons to do this. Now, the way that this helps, if you look at sodium, with this 1s2, 2s2, 2p6, 3s1 configuration, its valence electrons are the highest energy level electrons. So that means these 3s1. And this 1 electron, if we got rid of it, the sodium doesn't have no electrons anymore. Its valence electrons now become the second energy level, and sodium plus 1, that sodium ion, now has 8 valence electrons. The same thing happens with calcium, except it has 2 valence electrons in the 4th energy level. But all it has to do to get 8 valence electrons is lose those 2, and now calcium plus 2 has 8 valence electrons. They're just in the 3rd energy level there. So losing electrons can get you full, and that's easier for them than having to gain a whole lot of electrons to get full. Aluminum has its valence electrons in the s and p orbitals, but losing these 3 electrons we'll still get it to the noble gas configuration faster than trying to gain. So electronically, now this aluminum ion looks like neon. Inside, it still has those 13 protons that make it aluminum, but electronically on the outside to other atoms, it looks like neon, which means it's going to act and react like neon. Now, looking at our non-metals, those gain electrons to have a stable noble gas configuration, which means they're going to gain until they get 8. And these are much clearer and much simpler looking reactions and changes, because when fluorine becomes fluorine -1, it gains 1 electron, and it just goes from having 2p5 to 2p6. And gets that 8 valence electrons by gaining 1. Sulfur ends at 3p4, and so in order to get stable with a noble gas configuration, it needs to end at p6, and so it gains 2 electrons in order to get there. But notice, by gaining 2 electrons, it gets a negative charge, which is why I really shouldn't have written gaining as a plus sign. I'm trying to be very specific about that. But here we can see nitrogen turning into the nitrogen ion by gaining 3 electrons and getting a total of 8 valence electrons. So that's kind of the details of ion formation, but really it comes back to that octet rule and being able to predict things, charges, and how the electrons are going to change based on its position in the periodic table. So that's it. Have a good one.